talk is going to be from Vladislav. He's going to talk about the signatures of strong gravity and fast motions in polarization. So.
My name is Vladislav Loktev, PhD student in the University of Turku, working with Professor Yuri Poutine. I will talk about analytical models, methods to compute polarization, plane rotation, and other observable polarization parameters in general in case of Schwarzschild metric. Well, I feel as though I'm kind of a speaker lost in another neighborhood because I was about to focus more on the accretion disk around black holes, while this session is all about neutron stars. But on the other hand, the topic of my talk is about polarization parameters in Schwarzschild metric in general. So I'm going to be all vague and ambiguous about what kind of compact objects exactly I'm talking about.
Sorry for the interruption. Could you please speak a little bit louder because...
Okay, I will
okay.
try. Yes.
Thank you.
Is it better? Yeah. Anyway, first of all, as this has been mentioned, that X-ray polarization spectra carry important geometrical information, such as, again, for example, inclination of an X-ray pulsar or inclination of the accretion disk in X-ray binary, or the magnetic field structure in the disk, or basically anything about the geometry of the emission. And Schwarzschild metric often appears to be a good approximation of the space-time geometry around the compact objects. And again, if we have a neutron stars, of course, it is almost always a very good approximation. And for a black hole with a non-extreme spin parameters, or if an accretion disk is truncated enough so that the effects of spin are not very significant at large radii. And in this case, the computations of observable polarization parameters can be quickly performed using simple analytical relations, which can be effectively 100 or 1,000 times faster than to perform numerical ray tracing from scratch, especially if one's model has many geometrical parameters or configurations. Okay, now we'll review how this idea was applied to accretion second pulsars, and then about the accretion disk in X-ray binaries. Well, very quick recap of how the light bending looks like in Schwarzschild metric. So basically, the geodesics are planar, and the light trajectory lies in a plane, and the endpoints of it are connected with an integral equation of the light trajectory, which is here on the picture and the formula. At this point, some approximations can be used, such as the well-known, widely used Biloborodov approximation. But also, since last year, we have, in recent work of Yuri Poutine, we have even better approximation for light bending that gives very high precision for a wide range of angles. So using such analytical formulas and the Schwarzschild metric in the first place, the computation of observable polarization parameters is more or less straightforward, but more importantly, very quick, and moreover, it is, so to say, explicit because we compute light bending from any point in space-time towards any given observers at infinity. And in a paper that was actually precedent to this work, we applied this idea to accreting millisecond pulsar. And the point was to take into account the geometrical effects of the oblate shapes of the neutron star due to its fast rotation, and the pulse profiles for the spherical, well, as it has been already mentioned, for spherical moderately rotating neutron stars, so the results were already performed by Vironen and Poutinen in like 15 years ago. And the effects of oblateness is expected affect the polarization parameters, the pulse profiles, and well, So we have basically two stages where a polarization frame effectively rotates. The general relativity effects due to the gravity of black hole, neutron star, and the special relativity effect because millisecond pulsars have velocities of the surface relativistic. And also we need to take into account the oblate shape at some point in between. And all the analytical formulas for polarization plane rotations is derived as given on the slide appear to be rather simple. I will, here's some pulse profiles from that paper, and I will only say probably that the effects of the oblate shape is more significant than the effects of the spin the effects on the space-time metric in this problem, and the polarized pulse profiles were computed quickly and precisely, and I think more on the millisecond pulse profiles you will hear from Tuomo Salmi just before the short break. So in the meantime, I will inconspicuously slide to the black holes, but I will also keep it very brief. So the same idea can be applied to an accretion disk around a black hole. Here, I also show analogous formulas for the special and general relativity effects on the apparent polarization angles. The formulas are just for the most standard configurations, which is disk is thin, resided in the equatorial plane. The motion of the fluid is circular with Keplerian velocities. But such thing can be done for any other kind of surface of the disk, velocities, and source of the intrinsic polarization. So actually, the formulas for computing the polarization parameters are quite general. And I have some time. So I wanted to demonstrate the effects we are after in the inner edge of the disk. So it's 3 Schwarzschild radii in case of Schwarzschild black hole. Here, only thing worth pointing out is that the special relativity effect includes the jar effects itself, and they are drastically different between the Schwarzschild metric and flat space-time. Also, we have some funny pictures. So this overall impression of the effects. One thing to see here is that the dotted lines denote the difference in rotation with use of the approximate formulas, and practically they are invisible in most cases. And we also study the nature of the such errors connected to the use of the approximate formula. They basically act in the difference direction, as you can see in the bottom panels. They act in different ways in different radii, and we expect that overall errors when computing the spectrum will be even smaller than that. But this is again the example for polarization angle, but this is basically calls the same for the polarization degree and the flags. And this is the result overall spectrum of the accretion disk. And for the use of the approximation formula, as you can see also on the bottom panels, it's also justified because the errors are nearly non-existent. So, and for polarization degree, such spectra also gives like very small errors. And I also have a couple of minutes then. This was only about the effect of the use of the approximate formulas in Schwarzschild metric, but we can also look at the on the effect of the spin of the black hole if it exists. That is also going to be in a paper soon. And here shown the inner regions of standard accretion disk, as would be apparent on the image plane. And the green sticks depict the degree of expected polarization, assuming electron scattering atmosphere. Their lengths are the as the polarization. The length is polarization degree, and the angle is polarization plane rotation with direction. And the left is spin 0.5 and the right is spin 0.8. So I would say that quite a big spin here. And from the moderate inclination of 60 degrees. And here is the same for a higher inclination of 80 degrees. So in the right panel now also some purple sticks are now apparent. So basically they are the same, but computed to the numerical ray tracing, accounting for this spin of the black hole. So the green ones are computed with Schwarzschild approximation, and this also was the case on the previous slides, but we're hard to notice this purple because basically the Schwarzschild approximation works really good. And on this slide, a bunch of polarization spectra showing the polarization degree and polarization angle versus spectral energy are given for different parameters of the system, namely the spins and the inclination. And there is a lot of the thing to look at, but I would rather only draw your attention to the fact that for the moderate spin parameters, 0.5 and less, and non-extreme inclinations such as 60 degrees and less, the computed spectra are very close and can probably even be used in continuum fitting in order to infer the black hole spin. Although I will quickly wrap up. So to conclude, this all was meant only to encourage to use the analytical methods in Schwarzschild metric for quite variety of problems. They are often very applicable and accelerate the computation, especially when the geometry is varied. For example, also if we going to consider also processing disk, for example, then it will be quite time consuming to compute ray tracing for every inclination. And this is only for one model. So it will be significantly faster to compute such things quickly in Schwarzschild and already have some constraints on the geometrical parameters. Well, I think that's it. So thank you very much.
Thank you.